Hello, this is the last part of the lecture for this particular module of this course. In this lecture, we will be talking about the differences between artificial intelligence and traditional statistics. They're not the same thing. Given the fact that historically, traditional statistics, is a science that is based on data. After AI and machine learning came to the surface and became so important and showed that it is a data-driven technology, at the beginning, actually, back in 80s and early 90s, even prior to that, statisticians were the ones that were very against AI and machine learning, and there were a lot of interactions between them. At the time, AI and machine learning mainly was generated, and it was moving to the top by electrical engineers in many universities. And they found out that there's a lot of resistance against them by statisticians. It took a while until a statistician came to the conclusion that there is not much they can do against AI. So they changed their behavior, and then said, okay, AI is actually statistics. And it got to a point that even machine learning, the supervised machine learning, sometimes later started being called statistical learning. So anyways, in this lecture, we'll talk about the differences between these two technologies. Just because they use the data, it doesn't mean they do it in the same fashion. Let's start by talking about two different ways of approaching data and the reasoning, the way people do the reasoning. It's deductive reasoning versus inductive reasoning. Inductive reasoning talk about learn by following an intuitive pathway from general to specific. This is, they call the big picture people. That's a Platonic approach to the truth. And data analytics, AI and machine learning uses this approach, a pathway from general to specific, and it is inductive reasoning versus deductive reasoning, which is to learn by following intuitive pathway in exactly the opposite direction, going from specific to general. And they're known as detail people. That is the Aristotelian approach to the truth, and statistics uses that approach. So philosophically, statistics and AI and machine learning are very, very different from one another. That's one example, and I continue speaking about that. One thing it is true is that both statistical analysis, traditional statistics, and AI and machine learning, data analytics, they operate on patterns. However, when you use a statistical analysis, or a statistician, when they try to do that, they start with a predefined pattern. It's called a parametric model. And they compare the data and the observation and the measurements to the standard metric of the model that they have already decided what's going to be. And they're going to, of course, change that decision, keep going until they find the pattern that matches that. And they're testing the hypothesis in that fashion. In AI and machine learning and data analytics, the approach is completely opposite. In AI and machine learning, we do not start with a pattern, a predefined pattern, or an equation and try to find out how the data that we have received matches which one of them. In AI and machine learning, you build the model based on the data. You don't start with a model, you start with the data and you build a model based on data. So in deductive reasoning, the traditional statistic, you start with the theory, you confirm the hypothesis that you come up with, and then you arrive at conclusion. Whereby in AI and machine learning that you use inductive reasoning. You start with data and you infer conclusions from the data that you have based on the model you build. And then you arrive at conjecture, which is conclusion formed on the basis of incomplete information. In deductive reasoning, you start with a general principle and then you go forward toward the specific or special cases. In inductive reasoning, AI and machine learning, you start with a lot of special cases and you use them in order to come up with a general principle. So that is the difference between these two technologies. Traditional statistics is not new. It's been around for more than a century. The term statistics originally started in Germany in 1949 by Gottfried Achenwald. At the beginning of the 20th century, William Gossett developed the method for decision making based on small set of data. And that's where the statistics, traditional statistic, goes to. AI and machine learning, the way it's been used today, literally started in 1986. To understand the difference between traditional statistics and AI and machine learning, I strongly recommend that if you're interested in this, follow this paper and this book. This paper, the two cultures, statistical science, was published, excuse me, in 2001 by Leo Breiman, who actually was a statistician. He passed away, and he was a professor of University of Berkeley. And this paper that he has written is a fantastic paper, and it provides you with a good background of what is the difference between these two technologies. And after you read that, and if you become interested, then there is a book called Statistical Analysis and Data Mining Applications, written by Nisbet, Elder, and Miner, and that provides a lot more detail. So in general, both statistics and machine learning, they're trying to model, let's say, a physical phenomenon, something in nature, something that they're trying to find out. It's an unknown function that is represented, that represents the reality. However, we don't know what that function is. We're trying to model it. How do we do that? We start by collecting data from that particular reality. And when you do statistics, you take that data and you take it to a set of hypotheses, a set of equations, linear regression, nonlinear regression with very specific characteristics of a logarithmic equation or exponential equation, or whatever it is. You make the predetermined identification of the characteristics of that hypothesis, that equation that you have. So you take a set of those, and then you finally come to the conclusion that this data matches this particular correlation, this particular equation. And the difference is, if you do machine learning, you don't do that. You use learning algorithm, you use open computer programs, and you fit the data to it, and you ask, or what you do, you try to identify what combination of characteristics of these parameters that exist based on the data can generate not a single equation, but maybe a whole series of equations that may change as a function of space and time. Very, very complex. Therefore, it's not really an equation. It's a series of matrices of input and the connection of these input to the other neurons, the weights. And that's the final representative model that you come up with. In the statistics, it's fitting the data to predetermined equation, whereby machine learning is the job is to discover complex patterns based on the data that you have. And if you look at the technologies that exist, one thing we have to mention is that, for example, the traditional statistics is things such as linear regression, logistic regression, multivariate regression, Bayesian, network, Markov chain, support vector machine, and so forth, while artificial intelligence machine learning algorithms are supervised learning, unsupervised learning, end-to-end learning, reinforced learning, transfer learning. There are neural networks and fuzzy set theory, genetic algorithm, and all of that stuff. So while traditional statistical algorithms are not part of the machine learning, many of these traditional statistical algorithms can contribute to certain machine learning algorithms. So it is a good idea to learn and to understand them, but it's very important not to call linear regression or logistic regression machine learning algorithm. When people say things like that, it's one of the two. They either do not have the correct understanding of the technology, or if they do and they know this difference, they're trying to do some sort of a marketing scheme rather than reality. Another issue that separates these two technologies is the difference between correlation and causation. They're not the same thing. Just because you have correlation, it doesn't mean one is causing the other when you correlate two parameters. When a statistical analysis are presented to engineers and scientists, one of the most contentious issues that is usually brought up is the relationship between correlation and causation. Engineers and scientists usually mention that these two are not necessarily the same. Just because you see correlation between the two things, it doesn't mean one is causing the other one. So the question is that correct? Are engineers correct by saying that? The answer is absolutely yes. Let me show you some examples. Here, you're looking at two different phenomena. One is the US spending in science, space, and technology, and the other one is the suicides by hanging, strangulation, and suffocation. And if you look at the pattern of these two, do they correlate? Yes. From 1999 to 2009, they have a 99.2% correlation between these two. But is one causing the other one just because they correlate with one another? How about divorce rate in the state of Maine and per capita consumption of margarine? Is one causing the other one? But do they correlate with one another? Yes, 99.3% during that period of time. And finally, the US crude oil import from the country Norway from 1999, from 2000 actually to 2009, it highly correlates with drivers that are killed in collision with railway trays. Higher than 95% correlation. But is that the cause of the other one? So that clarifies that, and we will teach courses that explains the AI and machine learning and causation, which is very, very different from statistical analysis. One last thing we're going to talk about very quickly before we finish is this master's degree that you're taking, the certificate, which is Petroleum Data Analytics. Let's define what it is. Petroleum Data Analytics is the application of AI and machine learning in upstream oil and gas. However, it is very important to know that in the context of petroleum data analytics, AI and machine learning in oil and gas, There is a difference between data analytics and big data analytics. It has to do with the amount of data that's available to you that you want to build the model with, perform the analysis. In data analytics is using current existing data to build the model for optimization and decision making. Because this is the data that historically was collected even way before AI and machine learning, but the data exists. And the question is, can you use that data to build model using AI and machine learning? The answer is absolutely yes. And that's called data analytics. Big data analytics is using real-time data to build models for optimization and decision making. When you say real-time data, that means now you have sensors that can provide measurements every few seconds, and then you end up having gigabytes and terabytes of data. And the approach that you have for big data analytics is different from data analytics. So calling petroleum data analytics as artificial intelligence application in oil and gas industry, therefore you have data analytics and you have big data analytics. In the context of data analytics, usually it applies to completion engineering and to reservoir engineering, while big data analytics can be applied to drilling engineering and production engineering. And formation evaluation or reservoir characterization, that comes in the middle. I will explain in a second. Why is that? Because sometimes you can have a lot of data for that. For example, in data analytics, which is reservoir engineering and the completion engineering, you have historical production, injection, operational constraint, core analysis, well test, completion design, hydraulic fracturing, and workover. All of that data is a lot of data sometimes, especially when you have a mature field. But it's not enough to use the technology of big data analytics. And when I say that, there's not a lot of difference, but the approaches from an engineering point of view is a bit different. And not in this course, but in other courses that we teach, you get a lot of detail. And that what do you mean? You still use neural network, for example, to build a model in both cases. But the hyperparameter that you use and the way you approach solution is going to be quite different between these two. In big data analytics, when you have drilling engineering and production data, you have MWD and LWD. You have distributed acoustic sensors data or temperature sensors data. You have SCADA, you have ESP, you have seismic attribute, real-time pressure and temperature, and production. And when it comes to formation evaluation or reservoir characteristics, then you have well logs. And a lot of time you have a lot of data in well logs, so you could bring it in the middle and use the big data approach as well in here. And sometimes when you do artificial lift, then again, it is possible for you to have a lot of data. Very quickly, engineering application of AI is a purely data-driven modeling technology, which is the engineering approach to this technology. And its requirement is to making sure that physics is honored, what we call explainable AI. And its requirement also is definitely engineering expertise. Domain expertise is incredibly important. Also, expertise in AI and machine learning. Just because you're an engineer and you take one course or you watch a YouTube channel, YouTube video, doesn't mean because you understand the mathematics behind AI, then you become an AI expert. That's not what it means. Unfortunately, some people think that. AI expertise means you have to do a lot of practice to become an expert. How do you become a reservoir engineering expert? Not by reading a book, not even by getting a master's degree. You have to have a lot of experience. The same is true with AI and machine learning expertise. You have to make sure that physics is honored, geology is honored, and you have to make sure you can validate it, and you, to a large extent, you will see you have to use intelligent agents. Now, also, there is equation-based data-driven modeling. We call it smart proxy modeling. That's where your data comes from, a numerical simulator. A numerical simulator is based on a lot of equations that have been solved numerically, and you can generate a lot of data. So that exists too. That is not a purely data-driven modeling. It's using equation to generate the data. It is data-driven, but the source of the data is not nature, is not reality. It is equations from analytical or numerical solutions. So these are two different things. They're not the same thing. That's why combining these two things that people call hybrid model, it's literally a lack of expertise, either in AI and machine learning or engineering. If it's statisticians that are doing this, then it's because they say, if statisticians say hybrid model, it's because they have very superficial understanding of engineering problem that they're trying to solve. And if engineers call this hybrid model, it's because they have a very superficial understanding of AI and machine learning. So combination of these two is a very negative thing. And to a large extent, it could be purely a marketing scheme rather than has anything to do with reality. Finally, this is the last slide that I'm showing with you. It's artificial intelligence. If you want to find out how good you are in artificial intelligence, find out how interested you are in philosophy, find out how interested you become in neuroscience and in computer science. Because if you're not very interested in these technologies, in these sciences, then maybe your understanding and your interest in AI and machine learning is not really the way it's supposed to be. And of course, beside that, you have to know statistics, you have to know mathematics and biology. With that all said, I hope you enjoyed the rest of this course. Thank you very much.